All right, let's jump right in. We're going to tackle a really critical question today. How in the world do you find the weakest link in a system that just never, ever stands still? From the power grid we all rely on to our social feeds, our world is basically built on these networks that are in constant motion. So let's figure out how to keep them safe.
So let's start with a bit of a riddle to get us thinking. What could possibly connect a swarm of autonomous robots, the massive grid that powers our cities, and, say, the friend list on your favorite social media app? I mean, they seem totally different, right? But they actually share this really fundamental vulnerability.
And the answer is, they all have these hidden critical failure points. We're talking about single points of failure that, if they go down, could literally shatter the entire system, breaking it up into these little disconnected islands. And as you can probably imagine, the stakes there are incredibly high.
Now, the technical term for these weak spots is an articulation point, or you'll just hear it called an AP. Just look at the diagram here. If you pull out that one central red node, boom, the network just shatters into separate pieces that can't talk to each other anymore. So yeah, finding these APs is absolutely crucial for keeping a network healthy and robust.
But, okay, here's the huge catch. This whole problem has a major complication. We're not just dealing with some fixed puzzle that you can solve once. Nope. We are dealing with a constantly moving target because these networks, they're always changing.
I mean, just think about it for a second. In a system with a bunch of robots, those robots are moving in and out of range of each other all the time. In a social network, people are friending and unfriending each other constantly. And every single time a connection is added or taken away, the entire map of weak points can just shift instantly. The articulation point from a second ago might be totally safe now, and a brand new one could have just popped up somewhere else.
So, how have we typically tried to deal with this? Well, the old methods were frankly a bit like using a sledgehammer to swat a fly. They were designed for static, unchanging networks, and they run into some really big problems in our super dynamic world.
You see, the old way pretty much required a global reset. Every time one single connection changed, the entire network had to be reanalyzed from scratch. This is just incredibly slow, it wastes a ton of resources, and, this is a big one, it often requires some central authority to have a full map of the network, which, as you can guess, creates a huge privacy nightmare.
And the researchers behind this paper put it perfectly with this quote. By the time you've even finished your big global reset to map out the network, it's already changed again. Your information is, as they say, perpetually out of date. That sledgehammer is just way too slow for the job.
So what's the alternative? Well, this research proposes a really elegant idea. It's called the change flag solution. And it's all about how a tiny, local message can create this ripple of intelligence that spreads through the network.
Right, so instead of some global alarm that screams, "Everybody stop and recalculate," this method is way more subtle. When a connection changes, the two nodes that were directly involved create a small digital message. That's the change flag. And then this flag just spreads out locally, kind of like a ripple in a pond.
Okay, let's walk through the steps, because it's actually pretty simple. First, a connection, what we call an edge, gets added or deleted. Second, the two nodes right there at the scene of the event, they generate a unique flag. Third, that flag starts propagating outward to their neighbors, and then to their neighbors' neighbors in waves. And finally, and this is the absolute key, only the nodes that get touched by this ripple have to update their status. Everybody else, they just carry on like nothing happened.
The best way to think about it is like this. It's the difference between erasing one little number on a massive whiteboard versus wiping the entire board clean just to make one tiny change. It's obvious, right? This new way is targeted, it's efficient, and it is unbelievably fast.
So why does all this matter? Beyond the cool theory? Well, it's about building networks that are fundamentally smarter, faster, and maybe surprisingly, a whole lot more private.
I mean, just look at this. The amount of communication and raw computation you need for a global reset is just massive. But with an incremental update, the overhead is tiny in comparison. And that's because you're only waking up the parts of the network that actually need to know about the change. And man, is it fast. In one of the paper's simulations, a really critical link failed. That change flag rippled out, and the entire network had fully corrected itself. It correctly identified the whole new set of weak points in just 6 steps. 6. That is basically real-time adaptation. But here's a benefit that, in a lot of situations, might be even more important than the speed, and that's privacy. This new method has privacy baked right into its design from the ground up. So here's how it works. It's actually pretty clever. Instead of nodes sharing their entire list of connections, they only share really basic info about their distance to other nodes. It's kind of like telling a friend how many steps it is to the grocery store without handing over your entire address book. And because of this, no single node can ever reconstruct the full network map. From any one node's point of view, two completely different network layouts could look exactly the same.
So, the key takeaways here are super clear. This new approach is way smarter because it adapts locally, it's way faster, converging in just a handful of steps, and it's so much more private because it protects the network's overall structure. And what you get at the end of the day is a much more robust system that can constantly and efficiently monitor its own health.
And this all leaves us with one last really crucial thought. As everything from our cars to our homes gets more and more connected, maybe the goal isn't just to build systems that never break. Maybe the real key is to build systems with this kind of local intelligence, systems that are actually smart enough to heal themselves.